Hello guys, welcome back to my channel. And if you're new here on this channel, I'll be doing IGCSE Physics content. So I'll be doing past papers, topic questions, walkthrough, and also different kind of revisions. So if you're new here and you have your IGCSE Physics coming up anytime soon, make sure to subscribe so you won't miss any more content. So in this video, I'll be going through the first paper for the May June 2024, variant 41. So the May June papers are finally released and I'll be going through all of them in time. So make sure to stay tuned. So let's start with this paper, paper 41. A long tube contains oil. A small ball is held at rest at the surface of the oil. At time 0, the ball is released and begins to fall vertically through the oil. Figure 1.1 shows the ball falling through the oil. Okay, as the ball falls to be, as the ball begins to fall through the oil, it accelerates. Define acceleration. Okay, so acceleration is the rate of change of velocity. Or in other words, you can say it's the change in velocity per unit time. And the formula for acceleration is the final speed minus the initial speed over time taken. Any of these answers would be fine. Part B. The mass of the ball is 0.0075 kilograms. Calculate the resultant force acting on the ball when it's accelerating downwards at 2.8 meters per second squared. Okay, so resultant force. So resultant force, the formula is mass times acceleration. So the mass is 0.0075 and acceleration is 2.8. So when you multiply these two, 0.0075 times 2.8, that would give us 0.021 newtons. That's our answer for B. Part C. As the ball falls, its speed v is recorded. Figure 1.2 is the speed time graph for the falling ball. Okay. Describe what happens to the acceleration between t0 and t 0.04 seconds. Explain why this happens. Alright. So this is a question about terminal velocity. So to explain this, first, at time 0, from time 0 until maybe time somewhere around here, the acceleration is constant. But after a while, when we look at it, so the gradient of a speed time graph represents the acceleration. So since the graph is something like this, the gradient is decreasing. So if the gradient is decreasing, acceleration is also decreasing. I mean, if the graph was something like this, acceleration would increase. So, but then acceleration is decreasing. That could be one of our points. So acceleration decreases. And after that, after around time 0.02, we see that it becomes a straight horizontal line. So when this happens, gradient is 0. So that means since gradient is equal to acceleration, acceleration is also 0. So we can say acceleration becomes 0. And then why this happens is because, okay, so as the speed is increasing, the resistive force also increases. So the ball is falling down. So if v, which is the speed, increasing, and then the resistive force is also increasing. So as the speed increases, the resistive force also increases until at some point the speed, okay, the weight or the downward force becomes equals to the upward force. And once they balanced out, there will not be resultant force. So the object will reach constant velocity or terminal velocity. So when writing that, we can say that as speed increases, the resistive force also increases. Then after that, the downward and upward force become equal. So the resultant force becomes zero. And then the object will reach terminal velocity. So, and then object reaches terminal velocity. Now, I don't think we'd be needing all this for just the 4 marks, but I'm explaining every single thing that's happening there so you'd understand it. But then only 4 of these points would be enough for the full marks. Part 2. By drawing a tangent on figure 1.2, determine a value for the acceleration of the ball at 0.01 seconds. So we know that the acceleration is equal to the gradient. So let me just remove everything here. So we just have to draw a line at 0.01, just touching the graph. That's what the tangent is. Wait, let me draw it again. So the line looks something like this. And after that, we find the gradient of the line because gradient is equals to acceleration. So the gradient is equals to change in y over change in x. So let's take 2 coordinates. So we can take this point over here, which is, so each one represents, the increment is by 0.022. So if over here is 1, 2, 3, 4, 5, over here is 0.03, 0.032, 34, 36. So this is 0.036, comma 0.01. That's one coordinate. We just have to find another one now. We can take this line, actually. This would be very easy, which is 0.02, comma 0. Now we take these 2 points to find the gradient. So it's 0.001 minus 0 over 0.036 minus 0.02. So that would be okay. I think I made a slight mistake. I switched up the coordinates. So if we go back to the graph, this coordinate is 0.01, comma 0.036, and this one is 0, comma 0.02. Sorry for the mistake. So if we take the change in y, which is y2 minus y1 over x2 minus x1, so our y2, you can take 0.036 minus 0.02, 0.036 minus 0.02, and that divided by 0.01 minus 0. So 0.01 minus 0. So when we punch that in the calculator, 0.06 minus 0.02, that would give us 1.6 meters per second squared. That's our final answer. Let's go to the next question. Question number 2. Figure 2.1 shows two identical trolleys, P and Q, held at rest on a frictionless horizontal surface. A load is fixed to trolley P. Okay, so this is trolley P, and we have a 1.5 kg load and a compressed spring in between, and then we have at our next troll, which is trolley Q. There's a compressed spring between trolley P and trolley Q. The trolleys are released. As the spring expands, it pushes the trolleys apart. Okay, the trolley Q moves to the right at a constant speed of 0.36. The mass of each trolley is 1.2 kgs. The mass of the load on the trolley P is 1.5 kgs. The spring has negligible mass. Calculate the speed at which trolley P moves to the left. Okay, alright. So let's just label the figure with the information they've given us. This is 1.2 kgs. This is also 1.2 kgs. So that means the sum of these two is going to be 2.7 kgs. So once the spring has decompressed, this trolley Q moves that side and this moves the other side. So this question is about conservation of momentum. So what we have to know is the momentum to the left. So the momentum to the left is equals to the momentum. Okay, the momentum to the right is equals to the momentum to the left. So momentum is mass times velocity. So mass times velocity of trolley Q equals to mass times velocity of trolley P. So if you find the momentum of trolley Q, that's 1.2, which is a mass, and the speed is 0.36. So it's 1.2 times 0.36. And for trolley P, that we know that the total mass is 2.7, so it's 2.7. We don't know the speed, so we can say 2.7 v. So we can divide both sides by 2.7, and when we punch that in the calculator, that would give us 0.16. So the speed is 0.16 meters per second. That's the speed of P. The kinetic energy of trolley Q when it moves at 0.36 meters per second. Okay, so formula for kinetic energy, it's half mv squared. So the mass is 1.2, so it's half times 1.2 times velocity is 0.36 times 0.36 squared. So when we calculate that, that would give us 0.077 and continue. So we can just write it as 0.078. That's our kinetic energy. So it's going to be in joules, of course. The next one, part B, state the energy transfer that takes place as the spring expands. So when the spring expands, in the spring is elastic potential energy. So we can say the energy transfer is from elastic potential energy to kinetic energy, because we already calculated the kinetic energy in the previous one, to kinetic energy. We can just write it as elastic energy. You don't have to write the potential part, but that's also fine. Let's move on to question number 3. Figure 3.1 shows a small block of ice floating in a beaker of warm water. State one way in which the motion of the particles in ice differs from the motion of particles in water. Okay. So in ice, they vibrate. The particles, they vibrate. And since they're very packed to each other, they're very close to each other, the molecules can't move freely, they only vibrate. But in water, the particles move freely throughout the liquid. Part B. Energy is transferred from the water to the block of ice. Alright. State the name of thermal process that transfers energy from water to ice. So that one is conduction, because the ice is in the water, it's in contact with the water, and since the ice is solid, the transfer of heat is through conduction. Part 2. Initially, there is 0.34 kilograms of water in the beaker, and the specific capacity of water is 4,200. Calculate the energy transferred from this water as its temperature decreases from 28 to 10. Alright, so the formula for energy, which is Q equals mc, change in temperature. So Q is the energy, so that is equals to the mass, which is 0.34 times C represents specific heat capacity, which is 4,200, and change in temperature from 28 to 10, that's 18 degrees. So, or 28 minus 10, that's going to give us 18 degrees. So 0.34 times 4,200 times 18, that would give us 25,704, or we can just write it as 26,000. That's our answer to two significant figures. Part 3. The temperature of the water near the ice decreases first. Explain how convection causes the temperature of all the water in the beaker to decrease. Alright. So to explain this, let me just redraw the diagram. So we have a beaker, the water, and the ice. So what happens is the ice is cold, the water is warm. So there are water particles on top. So when they're in contact with the ice, they become cooler. So whenever they're becoming cooler, their density increases. So the particles on top, they become heavier, or their density increases. So the reason why their density increases is like because when they're colder, that means they contract. So you know how when objects expand when heated, so it's the opposite. When they become cooler, the particles come together, so density increases. So our first point is density of particles close to the ice increases. And then after that, when the density increases, these particles, they move downwards. And let's say we have other particles which are warm. So these warmer particles, when the colder ones go back down, the warm ones, they go back up. So the cooler water decreases, or the cool particles sinks to the bottom. So the colder water sinks, and the warm water rises. So the warm water rises, the cold water sinks. So this keeps on happening and happening until all the water is at a constant temperature. So that's what happens, and that's how all the water is cooled by the ice. State what happens to the internal energy of the water as the temperature of the water decreases. All right. Describe the change in terms of energy of the particles. So firstly, we have to understand internal energy. So internal energy is the energy due to the kinetic energy or the motion of the particles and the potential energy, or depending on the position of the particles. So when the temperature decreases, that means the kinetic energy decreases. So the kinetic energy decreases. This is because the temperature decreases. So when the kinetic energy decreases, since internal energy is dependent on the kinetic energy, so internal energy also decreases. That's going to be our answer. Let's go to the next question. Question number 4. The length of a magnifying glass is a converging lens. So it's a lens like this. Figure 4.1 shows the length of a magnifying glass, its two focal points, f1 and f2, and its principal axis, alright? State what is meant by focal point, right? Okay, so the focal point is a point on the principal axis where the rays of light meet. So once they are like rays of light, they converge and they all meet at the point which is f2. So they all meet at a focal point, and that point is called a focal point. Part 2. A student is using the magnifying glass when he sees a magnified image of an object. Figure 4.1, mark a point x on the principal axis for a possible position of the object. Alright. And point E for a possible position of the student's eye. Alright. So they've told us that the image has been magnified. So the object can be over here maybe. And we mark this one X. And if the object's over here, so the light rays should pass through the lens. So that means the eye should be, the observers should be somewhere around here on the other side of the lens. And we mark that as point E. So point E. This is the observer, and point X, that's the position of the object. Underline two words in the list that describe the image produced in A part 2. So it's of course virtual. One of them is supposed to be virtual, and it's supposed to be upright too. I'll explain how. So let me just rewrite this. Let's say this is point X, this point X, and the object is like this. So what happens is we can draw ray diagrams. So the first one is supposed to go through the center of the lens, and the next one is supposed to pass through the focal point. It goes horizontal until the lens and bends to pass through the focal point. Something like that. So what happens is the image forms when these two lines meet. But as you can see, they'll never meet. They're parallel lines. So what we do is we draw virtual rays on the other side. So this two rays meet somewhere around here. So this is a new object now. As you can see, it's enlarged and it's upright, and it's also virtual because we used virtual rays. So it's upright and virtual. Part B. The refractive index of the glass used to make the lens is 1.5. The speed of light in air is 3 times 10 to the power of 8. Calculate the speed of light in the glass. So refractive index, which is 1.5, should be equals to speed of light in air over speed of light in glass, which we can call v. So rearranging this gives us v equals 3 times 10 to the power of 8 over 1.5. So the speed of glass in the speed of light in glass is 3 times 10 to the power of 8 over 1.5. So that would give us 2 times 10 to the power of 8. 10 to the power of 8 meters per second. That's the speed of light in glass. Part 2. State what happens to the wavelength of light as it passes through the lens, or as it passes into the lens. So when the light passes into the lens, the wavelength decreases. This is because the light is coming from, if this was a lens, light is coming from air and then entering into a glass. So it's refracted, and glass is denser than air, so that means the wavelength decreases when passing through a denser material. Converging lenses are used in spectacles or glasses to correct one problem with vision. All right. Say the name of the problem and explain how a converging lens is used to correct it. You may draw a diagram. All right. So the name of the problem is long-sightedness. I'll explain in a minute. So usually in long-sightedness, what happens is, let's say we have the eye, and the eye has its own lens, and then we have a retina over here. So we can see because the image of something, let's say, I'm very bad at drawing, but this is supposed to be a tree. The image of something passes through the lens of our eye and lands on the retina. But as you can see, because of the person has long-sightedness, if the object is too close, wait, let me redraw that. If the object is too close, the image would form behind the retina, so the person will have some kind of blurry vision. But if we put a lens in between, then it would converge before reaching the lens of the eyes, and then it would converge again, and then the image would form on the retina. So that means the person can clearly see. So what can we write on the explanation? We can say that the lens focuses the image on the retina, while without the lens, the image forms behind the retina. That's our explanation. Question number 5. Describe how longitudinal waves differ from a transverse wave. Right. So the main difference between a transverse wave and longitudinal wave is that vibration of the wave is parallel to direction of travel in longitudinal waves. But not in transverse. Not in transverse waves. So what this means is if we draw a longitudinal wave, so longitudinal wave is something like this. Again, I'm not the best drawer, but this will work. And a transverse wave is something like this. So for a longitudinal wave, the vibration is in this direction, and direction of travel is also in the same direction. They're parallel. But in transverse wave, vibration is up and down, so it moves up and down, but direction of travel is in this direction. So they're perpendicular in transverse wave, but parallel in longitudinal waves. And the other difference is transverse waves have crests and troughs. So the trough is the lowest point, this is a trough, and the crest is the highest point. But the longitudinal wave doesn't have those. Part B. Figure 5.1 represents a seismic wave produced by an earthquake. State whether this seismic wave is a P wave, primary, or an S wave, secondary. Justify your choice, right? Okay, so one thing we have to understand is that the diagram is a longitudinal wave. So that means it's a seismic P wave because it's longitudinal. So a P wave is longitudinal and a seismic S wave is transverse wave. That's what you need to know. Part 2. The wave represented in 5.1 has a wavelength of 1.2 times 10 to the power of 4 meter. Calculate the actual distance between point J and point K. Alright. So wavelength. So for a longitudinal wave, the wavelength is distance between two of the compressed part, which is called compression, or distance between two of these, and these are called refraction. So the wide spaces or the less dense spaces are refraction, and these are compressions. So if you can see that, we have one wavelength, and we also have half of a wavelength. So it's 1.5 of the wavelength. So we do 1.5 times the wavelength is 1.2 times 10 to the power 4. So that would give us 1.5 times 1.2 times 10 to the power 4, which would give us 18,000 meters. That's the actual distance. Part 3. The wave in part 2 travels through the ground at a speed of 4,600 meters per second. As the wave passes through a certain point, the ground completes 5 oscillations. Alright. Calculate the time it takes for the wave to pass. Show you're working. So for this one, we have to use the speed formula. So speed is wavelength times frequency. So we're given the speed, which is 4,600. We're given the wavelength in the previous part, which is 1.2 times 10 to the power 4. And then we have the frequency. So to find the frequency, we divide both sides by 1.2 times 10 to the power 4. So that would give us frequency is equals to 0.3 0.383. So that's our frequency, but we're asked to calculate the time. So time is equals to 1 over frequency, which is 1 over 0.383. So that would give us 2.6 seconds. But the ground completes 5 oscillations, and this t is for 1 oscillation. So we multiply that by 5, so 2.6 times 5, that would give us 13 seconds. So the total time is 13 seconds. Question number 6. Figure 6.1 shows an isolated metal sphere suspended by an insulating thread from the ceiling. Alright. The sphere is negatively charged. The charge on a sphere produces an electric field in the surroundings. State what is meant by electric field. So it's the space where an electric charge experiences a force. Part 2. Draw on figure 6.1 to show the pattern and direction of electric field produced by the charge on a sphere. Draw at least 4 lines by the charge on the sphere. Okay, so an easy way to do this is we know that the sphere is negatively charged. So whenever we're drawing electric field, we can think of it as the direction of positive charge. Now in reality, yeah, positive charge do not move, but then we can think of it as positive, which direction in which the positive charge would move. So if we draw the lines, they would move towards the sphere because the sphere is negatively charged. So at least 4 lines, so 1, 2, 3, 4. So this is a diagram, and it's always towards the sphere or towards the negatively charged object. If the sphere was positively charged, let's say this is positively charged, direction would be away from it, because if a positive charge would be repelled by another positive charge. But since it's negatively charged, it's towards the sphere. The magnitude of the charge of the sphere is 3.5 times 10 to the power of minus 10 coulombs. An earthed metal wire is touched against the surface of the sphere, and the sphere is discharged. State what happens in the wire as the sphere is discharged. Right. So when the sphere is discharged, electrons move through the wire. From the sphere. So that's going to be our answer. So if we have a wire and it's earthed, so the negative charges, all of them move through the wire, and the sphere becomes neutral, and all the negative charge is transferred through the wire. Part 2. It takes a time of 0.14 nanoseconds for the sphere to discharge completely. Alright, calculate the average current in the earthed wire as the sphere discharges. Alright, so current I is Q over T. Q is the charge, so T is the time taken. So 0.14 nanoseconds. We have to change that into seconds. So nano means times 10 to the power of minus 9 seconds. And our Q is 3.5 times 10 to the power of minus 10. So dividing this two, so 3.5 is 10 divided by 0.14 times 10 to the power of minus 9. That would give us 2.5 amps. That is our answer. let's move on to the seventh question. The electromotive force, or EMF, of a battery is 7.5 volts. What is define the term electromotive force? Okay, so electromotive force is the amount of electrical energy generated per unit charge. That's an EMF of a circuit. Part B. The battery is connected in series with a variable resistor and a 30 ohm resistor. Okay, the battery is made using 1.5 volt cells. Alright. Draw a circuit diagram that shows all the 1.5 volt cells connected to produce an EMF of 7.5, the variable resistor, and the 30 ohm resistor. Okay, so we have 1.5 volts of cell. So to make 7.5, we would need 5 of them. So we have one cell, two, three. So we have 1, 2, 3, 4, 5. Okay, we have 5 cells, and the battery is connected in series with a variable resistor. So the sign for a symbol for variable resistor, it's a resistor with an arrow and a 30 ohm resistor. So the symbol for resistor is just a box, and then we just complete the circuit. This is a logo. Part 2. The resistance of a variable resistor can be varied from 0 to a maximum of 150. Using the axis in figure 7.1, draw the graph to show how the current in the circuit varies with the resistance of the variable resistor as it increases from 0 ohms to 150 ohms. Determine and label the value of the maximum current on the y-axis. Okay, so to draw the graph, first we have to understand the relationship between current and resistance. So we know that V equals IR. If we rearrange to make I the subject, I equals V over R. So from this, we can see that the current is inversely proportional to the resistance. So if resistance increases, in this case it would increase from 0 to 150, the current decreases. And to represent an inversely proportional relationship, this is the curve we use. So the curve is going to be something like this, because to show that current is inversely proportional to the resistance, it is not going to be a straight line graph, because the value slightly decreases, or the gradient slightly decreases. So after that, they also told us to determine and label the value of the maximum current. All right. So the maximum current is when the resistance of the variable resistor is 0. So it's going to be on the y-axis. And when the value of the variable resistance is 0, okay, let's go back to this diagram. So we have 7.5 volts here in total. If this is 0, but this is 30 ohms, as they told us over here. So if we have 30 ohms, the total resistance is going to be 30 plus 0, which is just 30. And voltage is going to be 7.5 volts. So coming back to this formula, I equals the voltage, which is 7.5 over 30. So 7.5 over 30, we have 0.25. So the maximum current is 0.25 amps. That's the maximum current. This was a pretty tough question. Question number 8. The isotope of thallium is radioactive. It decays by beta decay. Thallium 208 decays to an isotope of lead. Complete the equation for this decay. So first of all, for a beta decay, an electron is released. So this beta particle, it has no mass. So the mass number is 0, and since it's an electron, it's -1. So now we can just complete the equation. So the sum of what's on the right should be equal to the sum of what's on the left. So on the mass number, we have 208, the beta particle 0, so this is also going to be 208. And the bottom part, we have 81 here, and since we have -1, the lead should be 82. So 82 minus 1, that would give us 81. So it's balanced, or the numbers are the same on both sides. Part 2. The beta emission of thallium-208 is accompanied by a gamma emission from the nucleus. Explain why this emission does not affect the number in the equation. Okay, because let me try to redraw that. Because this is a gamma particle, it has no mass. So no mass means it doesn't affect the upper number, or this number, these two numbers over here, since it has no mass, and has no charge. So it won't affect the bottom numbers over here. So that's our answer. Part 3 suggests one reason why a nucleus of thallium-208 is unstable. Now there are multiple reasons why a nucleus could be unstable. One of them is nucleus is too heavy. That's one of the reasons. Or too many neutrons. So we can write any one of them and you'll get full marks. Part B. A sample of thallium-208 is placed in a thick lead container. Figure 8.1 shows a narrow beam of beta particles, gamma radiation, emerging from a small hole. Okay, in one side of the container. The narrow beam enters a region where there is a magnetic field that is directed into the page. Okay. On figure 8.1, draw a labeled line B to indicate the path of the beta particles in the magnetic field. And draw a labeled line Y to indicate the path of gamma radiation in the magnetic field. Okay. So we have the magnetic field, and magnetic field is into the page. So using Fleming's left-hand rule, we can determine which way the current or the charge is, in which direction. So one thing is for sure, we discussed that the gamma ray has no charge or no mass, so it's not affected. So what we can do is just a straight line, and we can label that Y. And next, the beta particle. So using Fleming's left-hand rule, if the magnetic field is into the page, that indicates that the direction of the current is this way, downwards. So what this means is, whenever we're looking at Fleming's left-hand rule, we consider convectional current. So the top part is a positive part, the bottom part, wait, I reversed it. So since the current is going to be moving downwards, that is from the negative terminal to the positive side. And we know that a beta particle is negatively charged. So since it's negatively charged, it's deflected or attracted to the positive side. So it would be like this. And that's the beta particle. Question number 9, and I believe this is the last question. The Sun is one of many billions of stars in the Milky Way. The Sun emits a very large quantity of energy as electromagnetic radiation. State 3 regions of electromagnetic spectrum in which the Sun emits the most energy. Okay, so 3 regions of electromagnetic radiation spectrum of the electromagnetic spectrum in which the Sun emits the most energy. So from this, the first one is obviously ultraviolet ray. And the second one is infrared. And the third one is visible light. So these are the three regions of electromagnetic spectrum in which the Sun emits the most energy. Electromagnetic radiation from the Sun travels at a speed of 3 times 10 to the power of 8. The radiation takes 500 seconds to reach the Earth. Calculate the distance from the Sun to the Earth. Alright. So we use the speed formula. Speed is distance over time. So distance is going to be speed times time. So it's going to be 3 times 10 to the power of 8 times 500. So that would give us 1.5 times 10 to the power of 11 meters. Never forget the units. Approximately 4.6 billion years ago, the Sun formed an interstellar cloud of gas and became a stable star. Okay, describe and explain what happens as an interstellar cloud of gas forms a protostar. So this cloud of gas, what happens to it is there's high gravitational attraction. Not attraction, or high gravitational force. So due to this force, the cloud will collapse on itself. So we can say the cloud collapses. So this cloud of gas, it has high gravitational attraction. So because of it, the cloud collapses and there's an increase in temperature. And because of this, it forms a protostar. Now, describe and explain what happens as a protostar becomes a stable star. Now, this is just asking us about the life cycle of a star. So first is the interstellar cloud to form a protostar, and now from a protostar to a stable star. So when it becomes a protostar, the temperature has already increased, as I mentioned earlier. So when the temperature increases, there's going to be a nuclear fusion inside the star. So because of this nuclear fusion, there's going to be an outward force. So due to the fusion and the high temperature, of course, there will be an outside force. And this outside force balances with the high gravitational force, which is inwards. So there will be an outside force which balances with the inward force of gravity. And when these two forces balance out each other and they cancel out each other, a stable star forms. And that was the last question. So if you've enjoyed, make sure to like and subscribe. And if you have any comments or any questions, make sure to drop them down below. and thank you for watching. And on the next video, I'll be doing either the paper 43 or paper 42. So stay tuned.